So, here's something worth thinking about as you settle in tonight. Right now, wherever you are, whatever position you're lying in, there's a force pulling on every single atom in your body. It's pulling on the blanket draped over you, on the pillow under your head, on the air filling your lungs. It's been doing this your entire life, every second of every day, without once taking a break. And the strange thing, the really strange thing, is that for most of human history, nobody could explain what it was. They could feel it. They could see its effects everywhere. Drop a rock, it falls. Pour water, it flows downhill. Jump, and you come back down. Always down. But why? What was actually happening? That question, that deceptively simple question, has occupied some of the greatest minds our species has ever produced. And the answers they came up with are so much weirder and more beautiful than you'd expect. Let's start where it makes sense to start, which is with people just looking up. Because gravity, before it was a science, was an observation about the sky. Thousands of years ago, long before anyone had a word for force or mass or acceleration, people watched the heavens and noticed something peculiar. The stars moved. Not randomly, not chaotically, but in these slow, reliable arcs across the sky, night after night, season after season. The sun rose and set with a regularity you could set your life by, and people did. They planted crops by it, navigated by it, built calendars around it. The moon swelled and shrank in a cycle so predictable that ancient cultures from Mesopotamia to China to Mesoamerica tracked it with astonishing precision. But here's the thing. Mixed in with all that reliable motion were a handful of objects that didn't follow the rules. The Greeks called them planets, which means wanderers, because these bright points of light drifted against the background of fixed stars in ways that seemed almost willful. Sometimes they moved one direction, then slowed, stopped, and appeared to move backward for a while before resuming their original path. Mars was especially dramatic about this. You could watch it over a period of weeks and see it trace this strange looping path against the stars. And if you were an ancient astronomer trying to make sense of the cosmos, that kind of behavior was maddening. Now, the Greeks were remarkable thinkers, and they took a crack at explaining all of this. Aristotle, around 350 BCE, built a model of the universe that was, in its own way, quite elegant. He said that everything in the earthly realm was made of 4 elements: earth, water, air, and fire. Each element had a natural place. Earth's natural place was at the center of the universe. Water's natural place was just above earth, air above water, fire above air. And when you displaced something from its natural place, it would try to return. That's why a rock falls when you drop it. It's made of the element earth, and it's trying to get back to the center. That's why flames rise. Fire is trying to reach its natural place above the air. It's a beautiful, intuitive system. Makes sense, right? Heavy things go down because down is where they belong. And Aristotle went further. He said heavier objects fall faster than lighter ones because they have more of the element earth in them, so their desire to reach the center is stronger. A big rock falls faster than a small rock. A stone falls faster than a feather. And honestly, if you just watch the world casually, this seems obviously true. Drop a bowling ball and a crumpled piece of paper, and yeah, the bowling ball hits the ground first. Aristotle's physics felt right, which is one reason it lasted so incredibly long. We're talking nearly 2,000 years. 20 centuries of the Western intellectual tradition more or less accepting Aristotle's account of why things fall. For the heavens, Aristotle had a different system entirely. Up there, beyond the moon, everything was made of a fifth element, the quintessence, and it moved in perfect circles because circular motion was eternal and divine. The planets, the sun, the moon, and the stars were all embedded in crystalline spheres that rotated around the earth, which sat motionless at the center of everything. It was a geocentric universe, and it felt right too. You don't feel the earth moving, after all. You look up and see everything else moving around you. The simplest explanation is that you're standing still and the sky is rotating. But those wandering planets kept causing problems. Their motions didn't fit neatly into simple circular orbits around the Earth. So around 150 CE, a brilliant astronomer named Claudius Ptolemy, working in Alexandria, came up with a fix. He kept the Earth at the center, but he added these smaller circles called epicycles. Imagine a planet riding on a small wheel, and that small wheel is itself riding along the rim of a much larger wheel centered on the Earth. By adjusting the sizes and speeds of these wheels within wheels, Ptolemy could reproduce the apparent motion of the planets with remarkable accuracy. His system, laid out in a massive work called the Almagest, became the standard astronomical model for over 1,000 years. It was complicated, sure. Some versions required dozens of epicycles stacked on top of each other. But it worked, in the sense that it could predict where a planet would be in the sky on a given night, and that predictive power gave it enormous authority. Think about what that means, though. For well over a millennium, the best minds in the world believed that heavy things fell because they were seeking their natural place, that the Earth was the immovable center of creation, and that the planets moved on invisible crystalline spheres. And these weren't stupid people. They were working with the observations available to them, building the best models they could. That's how science works, even when it's wrong. You build the best story you can from the evidence you have, and you hold on to it until something better comes along. Something better started coming along in 1543 when a Polish canon named Nicholas Copernicus published a book that quite literally rearranged the universe, De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres. Copernicus proposed something that sounded almost absurd at the time. The Earth was not the center. The Sun was, and the Earth, along with all the other planets, orbited the Sun. Now Copernicus didn't wake up one morning and decide to overturn 15 centuries of astronomy on a whim. He'd been thinking about this for decades, quietly, carefully. He was a meticulous man, almost pathologically cautious. He circulated his ideas privately among a small circle of scholars for years before allowing them to be published, and even then, the book didn't appear until he was literally on his deathbed. Legend has it that a copy of the printed book was placed in his hands on the day he died, May 24th, 1543. He may or may not have been conscious enough to know what he was holding. Here's what's really clever about Copernicus's model. By putting the Sun at the center, he could explain that strange retrograde motion of Mars without needing epicycles, or at least without needing nearly as many. The reason Mars appears to move backward in the sky is simply that Earth, on its smaller, faster orbit, periodically overtakes Mars on its larger, slower orbit. It's like passing a car on the highway. As you pull alongside and then ahead, the other car appears to drift backward relative to the distant scenery, even though it's still moving forward. That's all retrograde motion is. A trick of perspective caused by the fact that you, the observer, are also moving. But Copernicus still clung to circular orbits. because circles were considered perfect, and he still needed some epicycles to make his predictions match observation. His model was simpler than Ptolemy's in some ways, but it wasn't dramatically more accurate. And it came with a huge conceptual cost. If the Earth is moving, why don't we feel it? If the Earth orbits the Sun, why don't the stars appear to shift position as we move from one side of our orbit to the other? Copernicus had answers to these objections, but they weren't entirely satisfying, and many astronomers of his era treated his model as a useful mathematical trick rather than a description of physical reality. The person who started to change that was a Danish nobleman with a metal nose. Tycho Brahe, born in 1546, was one of the most extraordinary characters in the history of science. He lost part of his nose in a duel with a fellow student, reportedly over a mathematical dispute, and wore a prosthetic made of brass, or possibly gold and silver, for the rest of his life. He kept a pet elk that allegedly died after drinking too much beer and falling down a staircase. He was flamboyant, arrogant, brilliant, and he built the most precise astronomical observatory the world had ever seen on an island called Haven, given to him by the King of Denmark. What made Tycho so important wasn't any grand theoretical insight. It was data, pure, painstaking, extraordinary data. Night after night, year after year, for over 2 decades, Tycho and his assistants measured the positions of the planets with a precision that was roughly 10 times better than anything that had come before. He did this without a telescope, mind you. The telescope hadn't been invented yet. He used enormous sighting instruments, some of them the size of a room, calibrated with obsessive care, and he recorded everything. The positions of Mars, Jupiter, Saturn, the Sun, the Moon, hundreds of stars, all mapped with an accuracy of about 1 arc-minute, which is 1/60th of a degree. That doesn't sound like much, but in the context of 16th century astronomy, it was revolutionary. Tycho himself proposed a compromise model of the solar system where the planets orbited the Sun, but the Sun orbited the Earth, which was clever, but ultimately wrong. The real payoff of his life's work came after his death, and it came through the hands of a man he'd hired as an assistant and with whom he had a deeply complicated relationship. That man was Johannes Kepler. Kepler arrived in Prague in 1600 to work with Tycho, who was by then the imperial mathematician to the Holy Roman Emperor. Tycho was protective of his data, almost jealously so. He doled it out to Kepler in small portions, keeping the full treasure locked away. When Tycho died suddenly in 1601, under somewhat mysterious circumstances, Kepler moved quickly to secure the observations, and then he did something with them that changed everything. Kepler was obsessed with Mars. Its orbit was the most troublesome, the one that deviated most from simple circular motion. He spent years, literally years, trying to fit Tycho's data to a circular orbit. He'd calculate, compare, find a discrepancy of 8 arc-minutes, and start over. 8 arc-minutes. That's a tiny sliver of sky, about a quarter the width of the full moon. A lesser scientist might have shrugged it off, called it close enough. But Kepler knew Tycho's data was accurate to within 2 arc-minutes. An 8 arc-minute error wasn't noise. It was real. Something was wrong with the circle. And here's where Kepler did something genuinely brave. He abandoned the circle. After 2,000 years of astronomers insisting that celestial motion had to be circular, because circles were perfect and divine, Kepler looked at the data and said, no. The orbit of Mars is not a circle, it's an ellipse, a slightly squashed circle with the Sun sitting not at the center, but at one focus of the ellipse. This became his first law of planetary motion, published in 1609 in a book called Astronomia Nova. His second law, published in the same work, said that a planet sweeps out equal areas in equal times, which means it moves faster when it's closer to the sun and slower when it's farther away. And his third law, which came later in 1619, established a precise mathematical relationship between a planet's orbital period and its distance from the sun. The square of the period is proportional to the cube of the average distance. These three laws were extraordinary. They described the motion of the planets with unprecedented accuracy. But they were descriptions, not explanations. Kepler could tell you exactly how the planets moved, but he couldn't tell you why. What force was guiding them along these elliptical paths? What made them speed up as they approached the sun and slow down as they receded? Kepler himself suspected some kind of force emanating from the sun, something like magnetism perhaps, that pushed or swept the planets along. He was groping toward the right idea, but he didn't have the tools to get there. The tools would come from an unlikely place, not from an observatory, not from a nobleman's island, but from a farmhouse in Lincolnshire, England, where a young man had been sent home from university because of the plague. The year was 1665, and the young man's name was Isaac Newton. And Newton was, by almost any measure you'd care to use, one of the most extraordinary minds in the history of the human species. But here's the thing. In 1665, nobody knew that yet. He was 22 years old, recently graduated from Trinity College, Cambridge, with a degree that was frankly unremarkable. His professors hadn't singled him out. He hadn't published anything. He was just a quiet, somewhat difficult young man from a modest family, and when the Great Plague swept through England and the university shut its doors, he went home to Woolsthorpe Manor, his mother's farmhouse, and he stayed there for roughly 18 months. And during those 18 months, in that farmhouse, largely on his own, Isaac Newton laid the groundwork for calculus, developed his theory of color and optics, and began thinking seriously about the force that governs the motion of the planets. It's one of the most astonishing bursts of intellectual productivity in recorded history. Historians sometimes call it the Annus Mirabilis, the miracle year, though it was really more like a miracle year and a half. And the thing that makes it even more remarkable is that almost nobody knew it was happening. There was no fanfare, no announcement, just a young man sitting in a farmhouse, thinking. Now, you've probably heard the story about the apple. Newton, sitting under a tree, an apple falls on his head, and suddenly he understands gravity. And like most famous stories, this one is partly true and mostly embellished. Newton himself told a version of it late in his life. He mentioned seeing an apple fall from a tree and wondering why it fell straight down, toward the center of the earth, rather than sideways or upward. But there's no evidence it hit him on the head. That part seems to have been added later by Voltaire, who heard the story secondhand. What matters, though, isn't the apple. What matters is the question Newton asked next, which was genuinely revolutionary. He looked at the falling apple, and he looked up at the moon, and he asked, could it be the same force? Think about what a strange question that is. For thousands of years, people had treated earthly motion and celestial motion as completely different categories. Aristotle had built an entire cosmology around the idea that things on earth move according to one set of rules, and things in the heavens move according to another. The terrestrial realm was one of change and imperfection. The celestial realm was eternal and perfect. And even after Copernicus and Kepler had torn apart the old geocentric model, there was still this lingering assumption that whatever governed the planets was fundamentally different from whatever made an apple fall from a tree. Newton's genius was to suspect that they were the same thing. But suspecting it and proving it are two very different activities. And Newton didn't publish his theory of gravity for another 20 years. That's worth pausing on. He had the key insight in 1665 or 1666, and his masterwork, the Principia Mathematica, didn't appear until 1687. Part of that delay was Newton's personality. He was famously secretive, reluctant to publish, terrified of criticism. But part of it was that the mathematics needed to prove his idea rigorously simply didn't exist yet, and he had to invent it. That's what calculus was for. Newton needed a way to deal with quantities that were continuously changing, the speed of a falling object at every instant, the force of gravity at every point along an orbit. And the existing mathematical tools couldn't handle that. So he built new ones. Here's how the gravitational idea works, and it's beautifully simple in its statement, even though the implications are staggering. Newton proposed that every object in the universe with mass attracts every other object with mass, not just the sun pulling on planets, not just the earth pulling on apples. Every object, you and the chair you're sitting in, are gravitationally attracted to each other right now. The force is just incredibly tiny because neither you nor the chair is very massive compared to, say, a planet. But the force is there, and the strength of that force follows a precise mathematical rule. It's proportional to the product of the two masses. So if you double the mass of one object, you double the gravitational force, and it's inversely proportional to the square of the distance between them. That inverse square part is crucial. If you move two objects twice as far apart, the gravitational force between them doesn't just halve, it drops to 1/4. 3 times as far apart, 1/9 the force. 10 times as far, 1/100th. The force weakens rapidly with distance, but, and this is key, it never reaches zero. It extends, in principle, to infinity. Every mass in the universe is pulling on every other mass, right now, across all of space. The pull just gets vanishingly small over cosmic distances. Now, here's what's really clever about this. Newton took this simple law and showed that it explained everything. Kepler's 3 laws of planetary motion, which had been purely descriptive. Remember, Kepler could tell you how the planets moved, but not why. Newton showed that all 3 of Kepler's laws were mathematical consequences of the inverse square law of gravity combined with his own laws of motion. The elliptical orbits, the equal areas in equal times, the relationship between orbital period and distance, all of it fell out naturally from one simple force law. That's extraordinary. One equation, and suddenly the entire solar system makes sense. And not just the solar system. Newton showed that the same force that kept the moon in orbit around the Earth was the same force that made the apple fall. He actually did the calculation. He knew roughly the distance from the Earth to the moon, and he knew the moon's orbital period, about 27 1/3 days. From that, he could calculate the acceleration the moon was experiencing as it curved around the Earth in its orbit. And then he compared that to the acceleration of a falling apple at the Earth's surface, which Galileo had already measured. And when he accounted for the difference in distance, the moon is about 60 times farther from the Earth's center than the apple is, and applied the inverse square law, the numbers matched. The same force, following the same mathematical rule, operating at the Earth's surface and 250,000 miles away in space. It was one of the most beautiful confirmations in the history of science. The Principia Mathematica, when it finally appeared in 1687, was a thunderbolt. It's often cited as the single most important scientific work ever published, and honestly, it's hard to argue with that. In it, Newton laid out his 3 laws of motion. You know them, even if you don't think you do. An object at rest stays at rest unless acted on by a force. Force equals mass times acceleration. Every action has an equal and opposite reaction. And then, building on those laws, he presented his universal law of gravitation and showed how it explained not just planetary orbits but tides, the precession of the equinoxes, the trajectories of comets, and the shape of the Earth itself. The Earth isn't a perfect sphere, Newton predicted. It should be slightly flattened at the poles and bulging at the equator, because its rotation would cause material to be flung outward. And he was right. Measurements later confirmed it. But here's the thing about Newton's theory, and this is something that bothered people from the very beginning, including Newton himself. It described gravity perfectly. It told you exactly how strong the force would be between any 2 masses at any distance. It let you predict the motion of planets with stunning accuracy, but it didn't explain what gravity actually was. How does the sun reach across 93 million miles of empty space and pull on the Earth? What's the mechanism? Newton's theory treated gravity as what's called action at a distance. The sun exerts a force on the Earth instantaneously, across the void, with nothing in between carrying that force. And Newton found this deeply unsatisfying. He wrote, in a famous letter, that gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum, without the mediation of anything else. Is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. So even Newton thought his own theory was, in some sense, incomplete. He'd given the world the most powerful predictive tool it had ever seen, but he knew there was a deeper question lurking underneath. What is gravity? Not how does it behave, but what is it? How does it work? And he couldn't answer that. He famously wrote, "Hypotheses non fingo." I frame no hypotheses. He was saying, look, I can tell you the math, I can tell you the rules, but I'm not going to speculate about the underlying mechanism because I don't have evidence for it. And for more than 200 years, that was good enough. Newton's theory of gravity was so accurate, so powerful, so useful, that generations of scientists and engineers built their entire world on it. You could use it to predict eclipses to the second. You could use it to calculate the trajectories of cannonballs, the orbits of moons, the behavior of tides. When astronomers noticed that Uranus wasn't quite following the path Newton's equations predicted, they didn't doubt the theory. They assumed there must be another planet out there whose gravity was tugging on Uranus. And in 1846, 2 mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated where that unseen planet should be. Le Verrier sent his prediction to an astronomer in Berlin named Johann Galle, and Galle pointed his telescope at the predicted spot, and there it was, Neptune, a planet discovered not by looking through a telescope, but by doing math on a piece of paper. That's how good Newton's theory was. But there was one small problem, and it had been nagging astronomers for decades. Mercury, the innermost planet, the one closest to the sun, had an orbit that didn't quite match Newton's predictions. Its perihelion, the point in its orbit where it's closest to the sun, was slowly rotating, precessing, shifting around over time. And most of that precession could be explained by the gravitational pull of the other planets, But there was a tiny leftover amount, about 43 arcseconds per century, that couldn't be accounted for. 43 arcseconds per century. That's an incredibly small discrepancy. You'd barely notice it. Leverrier, the same man who'd found Neptune, tried the same trick again. He proposed that there must be another undiscovered planet, even closer to the Sun than Mercury, whose gravity was causing the extra precession. He even gave it a name, Vulcan. Astronomers searched for it for decades. Some even claimed to have seen it. But Vulcan didn't exist. The answer to Mercury's anomalous precession wasn't a hidden planet. It was a hidden flaw in Newton's theory itself. And the person who found that flaw was working in a patent office in Bern, Switzerland, around 1905, turning over in his mind a question that seemed almost childishly simple. What would it be like to ride alongside a beam of light? What would you see? What would happen to time, to space, to the very fabric of reality if you could somehow keep pace with a photon? His name was Albert Einstein, and in 1905 he was 26 years old, a technical expert third class at the Swiss Federal Patent Office, which is about as unglamorous a title as you can imagine for someone about to reshape the universe. He hadn't been a standout student in the traditional sense. He'd clashed with professors, struggled to find an academic position after graduating from the Polytechnic in Zurich, and had spent a couple of lean years tutoring and substitute teaching before landing the patent office job almost as a fallback. But here's the thing about Einstein that made him different from nearly every other physicist of his era. He thought in pictures. He didn't start with equations. He started with scenarios, mental movies, little thought experiments that he'd play out in his head with extraordinary rigor, and only then would he reach for the math to describe what he'd imagined. And that question about riding a beam of light, it led him somewhere astonishing. If you're moving alongside a beam of light at the speed of light, you should see the light wave frozen in place, right? A stationary electromagnetic wave just hanging there next to you. But Maxwell's equations, the fundamental laws of electromagnetism that had been established decades earlier, said that couldn't happen. There was no such thing as a stationary electromagnetic wave. The equations didn't allow it. So something had to give. Either the laws of physics looked different depending on how fast you were moving, or, and this was the radical option, the speed of light was the same for everyone, no matter how fast they were going. Einstein chose the radical option. In June of 1905, he published a paper called On the Electrodynamics of Moving Bodies, and it laid out what we now call special relativity. The core idea is deceptively simple. The laws of physics are the same in every inertial reference frame, and the speed of light in a vacuum is constant, roughly 300 million meters per second, for all observers, regardless of their motion. Now, you might be thinking, okay, that sounds reasonable enough. What's the big deal? The big deal is what follows from those two seemingly innocent postulates. If the speed of light is truly constant for everyone, then something else has to be flexible, and that something else turns out to be time and space themselves. Time slows down for objects moving at high speeds. Lengths contract in the direction of motion. Events that are simultaneous for one observer might not be simultaneous for another. And mass and energy are interchangeable. That's where E equals mc squared comes from a short follow-up paper Einstein published later that same year. It's all connected. Special relativity knits together space and time into a single four-dimensional fabric that Einstein's former mathematics professor, Hermann Minkowski, would later call spacetime. Minkowski gave a famous lecture in 1908 where he declared, Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Beautiful line. Einstein reportedly wasn't thrilled about it at first. He thought Minkowski was dressing up his physics in unnecessary mathematical finery, but he'd come around to appreciate it soon enough, because that geometric way of thinking about space-time turned out to be exactly the tool he needed for what came next. Because here's the thing about special relativity. It's called special for a reason. It only deals with the special case of uniform motion. Objects moving at constant speeds in straight lines, no acceleration, no gravity. And Einstein knew, almost immediately after publishing it, that he had to generalize the theory to include acceleration and gravity. He knew it because of something that had been hiding in plain sight in physics for centuries, something so obvious that almost nobody had thought to question it. Think back to what we talked about earlier, about Newton's laws. In Newton's framework, there are two different concepts of mass. There's inertial mass, which is how much an object resists being accelerated. Push a bowling ball and push a tennis ball with the same force, and the bowling ball accelerates much less because it has more inertial mass. And then there's gravitational mass, which is how strongly an object is pulled by gravity. The bowling ball weighs more because it has more gravitational mass. Now here's the strange part. These two kinds of mass, which are conceptually completely different things, always turn out to be exactly equal. Always. To extraordinary precision. Newton noticed this. He even tested it with pendulum experiments. But he had no explanation for why it should be true. It was just a coincidence, a convenient fact baked into the equations. Einstein realized it wasn't a coincidence. It was a clue. And the moment of insight came in 1907, while he was still at the patent office, in what he later called the happiest thought of my life. He imagined a person falling freely, falling off a roof, say, or floating inside an elevator whose cable had just snapped. That person, during the fall, would feel weightless. They'd feel no gravity at all. If they let go of a ball, it would float beside them, falling at the same rate. Inside that falling elevator, there would be no experiment you could do to distinguish your situation from floating in empty space, far from any gravitational field. Gravity and acceleration were, in some deep sense, the same thing. This is the equivalence principle, and it's the seed from which all of general relativity grew. Let that sink in for a moment. If you're in a closed room with no windows, and you feel your feet pressed against the floor, you genuinely cannot tell whether you're standing on the surface of the earth with gravity pulling you down, or whether you're in a rocket ship accelerating upward at 9.8 meters per second, squared in deep space with no gravity anywhere nearby. The two situations produce identical physics. Identical. Not just similar. Identical. And if that's true, then gravity isn't really a force at all. Not in the way Newton imagined it. It's something else entirely. Something geometric. But getting from that flash of insight in 1907 to a complete mathematical theory took Einstein 8 years of grueling, sometimes agonizing work. 8 years. And this is a part of the story that doesn't get told enough, because we tend to mythologize Einstein as this effortless genius who just saw the truth and wrote it down. The reality is messier and more human, and honestly, more inspiring. He struggled. He made wrong turns. He published equations that were incorrect and had to retract them. He nearly lost the race to someone else. The core mathematical challenge was immense. Einstein needed to describe how matter and energy curve spacetime, and how that curvature tells matter how to move. But the geometry of curved spaces, non-Euclidean geometry, the kind where parallel lines can converge or diverge, where the angles of a triangle don't add up to 180 degrees, was not something Einstein had mastered. He'd actually skipped some of those math classes back in Zurich. So in 1912, he turned to his old classmate and friend, Marcel Grossmann, who was now a mathematics professor, and essentially said, "Help me. I need the math." Grossmann introduced him to the tensor calculus developed by the Italian mathematicians Gregorio Ricci Curbastro and Tullio Levi-Civita, and to the Riemannian geometry that Bernhard Riemann had developed back in the 1850s. And here's a wonderful irony. Riemann had built this entire mathematical framework for describing curved spaces of any number of dimensions, largely as a purely abstract exercise. And now, more than half a century later, it turned out to be exactly the language the universe was written in. Einstein and Grossmann collaborated closely, and by 1913 they had a draft theory, the so-called Entwurf theory. But it wasn't quite right. The equations weren't generally covariant, meaning they didn't hold their form under arbitrary coordinate transformations, which Einstein believed they should. He wrestled with this for 2 more years. He moved from Zurich to Berlin in 1914, took up a prestigious position at the Prussian Academy of Sciences, separated from his wife Mileva, and threw himself into the problem with an intensity that left him physically ill at times. He later described this period as the most strenuous time of his life. And then, in the autumn of 1915, things came to a head in a way that reads almost like a thriller. The great German mathematician David Hilbert had become interested in the same problem. Hilbert was arguably the most powerful mathematician alive, and he was approaching the question from a more purely mathematical angle, using variational principles. Einstein and Hilbert were in correspondence, and Einstein realized with growing alarm that Hilbert might beat him to the correct field equations. The two were working in parallel, exchanging letters, and in November 1915, both were converging on the answer almost simultaneously. Einstein presented his final correct field equations to the Prussian Academy on November 25, 1915. Hilbert submitted a paper with essentially equivalent results around the same time. The exact priority is still debated by historians, though Hilbert himself always credited Einstein with the physical ideas. But what matters for our story is what Einstein did just a week before that final presentation. On November 18th, he used his nearly complete equations to calculate the precession of Mercury's perihelion. Remember that 43 arcseconds per century that had baffled astronomers for decades? That tiny, stubborn discrepancy that Leverrier had tried to explain with a phantom planet? Einstein's equations predicted it exactly. 43 arcseconds, no fudge factors, no adjustments, no hidden planets, just the geometry of curved spacetime around the sun. Einstein later told a friend that when he saw the result, he had heart palpitations. He was so excited he couldn't work for days. And honestly, can you blame him? For 60 years, this tiny anomaly had resisted every attempt at explanation within Newtonian gravity. And now, from a completely new theory built on completely different principles, the idea that mass curves space-time and objects follow the straightest possible paths through that curved geometry. Out popped the exact right number. It's one of those moments in the history of science where you just have to sit back and marvel at the sheer elegance of it, because this wasn't a theory designed to fix Mercury. Einstein wasn't sitting there tweaking parameters to match an observation. He started from a completely different place, from thought experiments about elevators and light beams and the equivalence of gravity and acceleration, and built a geometric framework for all of gravity. And then, almost as a side effect, it spit out the exact number that had haunted astronomers since the 1850s. That's not curve fitting. That's truth. But here's the thing about physics. One correct prediction, no matter how beautiful, isn't enough. Mercury's precession was a known problem. A skeptic could argue, unfairly, but they could argue, that Einstein had somehow reverse-engineered his theory to match that particular number. What general relativity needed was a prediction of something nobody had measured yet. Something new. Something that would either happen or not happen, and that Newton's theory said should go differently. And general relativity offered exactly such a prediction. It said that light itself should bend when it passes near a massive object. Now think about what that means. In Newton's universe, light doesn't have mass in the traditional sense, so gravity shouldn't really affect it. Actually, that's not quite fair. You could make a Newtonian argument that light might bend a tiny bit if you treat photons as particles with some effective mass, and if you work through that calculation, you get a specific deflection angle. But Einstein's general relativity predicted exactly twice that Newtonian value. Twice. Because in Einstein's picture, it's not just that gravity pulls on light, it's that the space itself is curved near the sun, and light follows that curvature. The extra factor of 2 comes from the curvature of space in addition to the curvature of time, and that distinction is purely a general relativistic effect. So if you could measure how much starlight bends as it passes close to the sun, you'd have a clean test. Newton says one number. Einstein says double that. Measure it, and you know who's right. The problem, of course, is that the sun is bright. Overwhelmingly, blindingly bright. You can't normally see stars that appear close to the sun in the sky because the sun's light washes everything out. But there's one situation where you can: a total solar eclipse. When the moon slides in front of the sun and blocks its disk, the sky goes dark for a few minutes, and suddenly you can see stars that are very close to the sun's apparent position. If you photograph those stars during the eclipse and then compare their positions to where they appear in the night sky months later when the sun is nowhere near them, you can measure whether their light was bent as it grazed past the sun. Einstein actually published this prediction in 1911, before he'd even finished general relativity. At that point, he was using an incomplete version of the theory that gave the smaller Newtonian equivalent deflection, about 0.87 arcseconds for a star right at the sun's edge. A German astronomer named Erwin Finlay Freundlich got excited about testing this and organized an expedition to observe the total solar eclipse of August 1914 from Crimea. And here's where history takes one of its darkest and strangest turns. Freundlich and his team traveled to Russia, set up their equipment, and then World War I broke out. They were in Russian territory as German nationals, and they were detained. Their equipment was confiscated. The eclipse observation never happened. And honestly, that was one of the luckiest breaks in the history of physics. Because if Freundlich had made the measurement in 1914, he would have been testing Einstein's earlier, incorrect prediction, the one that gave half the right answer. By the time Einstein completed general relativity in November 1915, he'd realized the correct deflection was 1.75 arcseconds, not 0.87. If the 1914 expedition had succeeded and found a deflection of 1.75 arcseconds, it would have seemed to contradict Einstein's prediction, and the whole theory might have been dismissed prematurely. The war, terrible as it was, accidentally saved Einstein from being proven wrong with the wrong prediction. So the test had to wait. And the person who eventually carried it out was Arthur Stanley Eddington, a British astrophysicist and one of the few scientists in England who actually understood general relativity during the war years. This is remarkable in itself. Remember, Britain and Germany were locked in a devastating war, and most British scientists wanted nothing to do with German physics. But Eddington was a Quaker and a pacifist, and he had a deep intellectual appreciation for Einstein's work. He'd learned about general relativity through correspondence with the Dutch physicist Willem de Sitter, who was in neutral Holland and could communicate with both sides. Eddington became general relativity's champion in the English-speaking world, and he recognized immediately that the next total solar eclipse, May 29, 1919, offered a spectacular opportunity, not just because the war would hopefully be over by then, but because of a remarkable astronomical coincidence. On that date, the Sun would be positioned right in front of the Hyades star cluster, one of the richest and brightest clusters of stars in the sky. That meant there would be an unusually large number of bright stars visible near the Sun's edge during totality. More stars meant more data points, which meant a better measurement of the deflection. Eddington organized 2 expeditions. One went to Sobral in northern Brazil. The other, the one Eddington himself joined, went to the island of Principe, off the west coast of Africa. Both teams carried telescopes, photographic plates, and careful plans for capturing images of the star field around the eclipsed Sun. The Principe expedition almost didn't work. The morning of May 29th dawned cloudy and rainy. Eddington was reportedly anxious, watching the sky, waiting. The clouds began to thin as the eclipse approached, and the team started taking photographs through gaps in the cloud cover. They got 16 photographic plates during the roughly 5 minutes of totality, though many were degraded by the clouds. The Sobral team had better weather and got clearer images, though ironically, their best telescope had a focusing problem due to the heat, and their most reliable results came from a smaller backup instrument. Over the following months, both teams carefully measured the star positions on their photographic plates and compared them to reference photographs of the same star field taken when the Sun wasn't present. The analysis was painstaking. They were looking for shifts of less than 2 arc seconds, which on the photographic plates amounted to tiny fractions of a millimeter. But when the results came together, they were clear. The Sobral data gave a deflection of about 1.98 arc seconds. The Principe data, despite the clouds, gave about 1.61 arc seconds. Both were consistent with Einstein's prediction of 1.75, and clearly inconsistent with the Newtonian prediction of 0.87. On November 6, 1919, the results were announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London. The room was packed. The Astronomer Royal, Frank Watson Dyson, presented the findings. The verdict was that Einstein's theory had been confirmed. Light bends in the gravitational field of the Sun by the amount general relativity predicts. And then, something happened that was almost as remarkable as the science itself. Einstein became a global celebrity overnight. The next morning, the Times of London ran the headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." The New York Times picked it up. Within days, Einstein's face was in newspapers around the world. Here was a German-born physicist in the immediate aftermath of a war that had killed millions, being celebrated by British scientists for a theory that overturned the work of Britain's greatest scientific hero, Isaac Newton. There was something almost redemptive about it, science transcending nationalism, truth mattering more than borders. Eddington, the British pacifist, confirming Einstein, the German-Swiss theorist. It captured the public imagination in a way that pure science rarely does. Now, it's worth being honest about the 1919 measurements. Modern reanalysis suggests that Eddington's data was actually not as clean-cut as it was presented at the time. The error bars were large enough that the results were somewhat ambiguous, and some historians have argued that Eddington, who was already convinced Einstein was right, may have been somewhat selective in which data he emphasized. This doesn't mean the conclusion was wrong. Subsequent eclipse measurements in the 1920s and beyond confirmed the result with increasing precision, and today we can measure gravitational light bending with extraordinary accuracy using radio telescopes and quasars. The deflection matches general relativity perfectly, but the 1919 result, the one that made Einstein famous, was more of a strong indication than a definitive proof. Science is sometimes messier than the stories we tell about it. Still, the conceptual revolution was real and irreversible. After 1919, the physics community took general relativity seriously as a description of how gravity actually works, and the implications were staggering, because Einstein's equations didn't just describe the bending of light or the precession of Mercury. They described the behavior of the entire universe. And this is where the story takes perhaps its most dramatic turn. Because when people started looking for solutions to Einstein's field equations, mathematical descriptions of how space-time could be shaped by different distributions of matter and energy, they found things that nobody expected, not even Einstein. The first person to find an exact solution was Carl Schwarzschild, and the circumstances are almost unbelievable. Schwarzschild was a German physicist and astronomer who, despite being over 40 years old, had volunteered for military service in World War I. He was serving on the Eastern Front in Russia, calculating artillery trajectories, when he read Einstein's November 1915 papers. And there, in the trenches of a world war, he worked out the exact solution to Einstein's field equations for the spacetime around a single, spherical, non-rotating mass. He sent the solution to Einstein in a letter, and Einstein presented it to the Prussian Academy in January 1916. Schwarzschild's solution was elegant and complete, and it described exactly how spacetime curves around something like a star or a planet. For most purposes, it gave the same predictions as Newton: objects orbit, things fall, the familiar gravitational behavior we see every day. But it also contained something deeply strange. At a particular distance from the center of the mass, a distance that came to be called the Schwarzschild radius, the mathematics did something peculiar. The equations seemed to blow up, to become singular. And if you imagined compressing all the mass inside that radius, the solution described a region of space-time so severely curved that nothing, not even light, could escape from it. Schwarzschild himself didn't fully explore what this meant. Tragically, he contracted a rare autoimmune disease on the front and died in May 1916, just months after his groundbreaking work. He was 42 years old, but the solution he left behind contained, hidden in its mathematics, the first theoretical description of what we would eventually call a black hole. Though that name wouldn't come along for decades. For a long time, physicists called them frozen stars, or collapsed objects, or just tried not to think about them at all. And honestly, most physicists in the early 20th century didn't take the idea seriously. Einstein himself was deeply uncomfortable with it. He spent years arguing that no real physical process could compress matter down to the Schwarzschild radius, that nature would find some way to prevent it. And you can understand why. The idea is genuinely unsettling if you sit with it. You're saying that there's a solution to the equations of general relativity, equations that describe how the actual universe works, where space-time curves so steeply that it essentially folds in on itself, creating a region that's causally disconnected from the rest of the universe. Anything that crosses that boundary, that invisible surface at the Schwarzschild radius, can never come back. Not because some force is holding it in, but because all paths through space-time inside that boundary point inward. Even the path that light would take, even time itself, in a sense, tilts toward the center. It's not a wall. It's not a barrier you slam into. It's more like, imagine you're walking on a landscape, and the landscape itself gradually tilts until every direction you can walk is downhill. There's no uphill anymore. That's what happens inside the Schwarzschild radius. Every direction through space-time leads deeper in. The boundary where this happens, the event horizon, as it was eventually named, is perfectly smooth. If you were falling into a sufficiently large black hole, you might not even notice the moment you crossed it. Nothing dramatic happens at the horizon itself. No wall of fire, no sudden crushing force. You just pass a point of no return that you can't detect locally. The strangeness is entirely in the global structure of space-time. But here's what's really interesting about the history. For nearly half a century after Schwarzschild's solution, the physics community was deeply divided about whether any of this was physically real. And the debate wasn't just hand-waving. Serious, careful physicists made serious, careful arguments on both sides. In 1939, J. Robert Oppenheimer, yes, the same Oppenheimer who would later lead the Manhattan Project, co-authored a paper with Hartland Snyder that showed, mathematically, what happens when a sufficiently massive star exhausts its nuclear fuel and collapses under its own gravity. They demonstrated that if the star is heavy enough, nothing can stop the collapse. Not the pressure of the atoms being squeezed together, not the quantum mechanical repulsion between electrons, nothing. The star just keeps falling inward, past the Schwarzschild radius, and forms exactly the kind of object that Schwarzschild's solution described. The paper is remarkable. It's clear, it's rigorous, and it essentially predicts black holes as a real astrophysical outcome. But then the war came, and Oppenheimer went off to Los Alamos, and the paper was largely forgotten for years. Meanwhile, other physicists kept pushing back. Arthur Eddington, the same Eddington who confirmed light bending in 1919, was one of the most vocal skeptics. He found the whole idea of gravitational collapse to a singularity philosophically repugnant. He argued against it publicly and sometimes rather harshly. There was a young Indian physicist named Subramanian Chandrasekhar, who, in the early 1930s, had calculated that white dwarf stars, the dense remnants left after ordinary stars die, had a maximum possible mass. Above about 1.4 times the mass of our Sun, a white dwarf couldn't support itself against gravity. Chandrasekhar presented this result at a meeting of the Royal Astronomical Society in 1935, and Eddington stood up and essentially ridiculed it, called it absurd, said there ought to be a law of nature preventing a star from behaving in such a way, and because Eddington was one of the most famous and respected astrophysicists in the world, his opinion carried enormous weight. Chandrasekhar was devastated. He eventually left England for the University of Chicago, partly because of how the British astronomical establishment had treated his work. He went on to have an extraordinary career, won the Nobel Prize in 1983. But the episode left scars. And here's the kicker. Chandrasekhar was completely right. That mass limit, now called the Chandrasekhar limit, is one of the most important numbers in astrophysics. It's the reason some stars end their lives as white dwarfs, and others collapse further into neutron stars, or, if they're massive enough, into black holes. So you had this situation where the mathematics was pointing clearly toward the existence of these extreme objects, and many of the best minds in physics were refusing to accept it. Which, honestly, is a pattern you see again and again in the history of science. The equations tell you something, and you don't want to believe them because the implications are too strange. The term black hole itself didn't appear until 1967, when the American physicist John Archibald Wheeler used it in a lecture. Wheeler was a fascinating figure. He had worked on the Manhattan Project. He had collaborated with Niels Bohr on nuclear fission theory, and he became one of the great champions of general relativity in the second half of the 20th century. Before Wheeler coined the phrase, people had been using clunky terms like gravitationally totally collapsed object, which, you can see why that didn't catch on. Wheeler's term was vivid, memorable, slightly ominous. It stuck immediately, and it changed how people thought about the concept. Sometimes naming something is itself a kind of breakthrough. Now, through the 1960s and 1970s, the theoretical understanding of black holes deepened enormously. Roger Penrose, a British mathematician and physicist, proved in 1965 that once gravitational collapse passes a certain point, the formation of a singularity, a point of infinite density at the center, is inevitable under general relativity. Not just possible, inevitable. This was a landmark result because it showed that singularities weren't artifacts of the perfect symmetry in Schwarzschild's solution. Even messy, asymmetric, realistic collapse leads to a singularity. Penrose won the Nobel Prize for this work, though not until 2020, more than half a century later, which tells you something about how long it can take for the significance of theoretical work to be fully recognized. And then there was Stephen Hawking, who took Penrose's mathematical techniques and ran with them in extraordinary directions. In the early 1970s, Hawking made a discovery that genuinely shocked the physics community. He showed that black holes aren't actually perfectly black. They emit radiation. This sounds like a contradiction. How can something from which nothing can escape emit anything? But the mechanism is subtle and beautiful. It comes from quantum mechanics, not from general relativity alone. Near the event horizon, quantum fluctuations in the vacuum, the constant fizzing of particle-antiparticle pairs popping into and out of existence, can get separated by the extreme curvature of spacetime. One particle falls in, the other escapes. The escaping particle carries energy away from the black hole, which means the black hole slowly loses mass. Very, very slowly, for any black hole of astronomical size. A black hole with the mass of our sun would take something like 10 to the power of 67 years to evaporate. That's a number so large it makes the current age of the universe look like the blink of an eye. But the principle matters enormously because it connects gravity, quantum mechanics, and thermodynamics in a way nobody had anticipated. Think about what that means for a second. Hawking showed that black holes have a temperature. They have entropy. They obey thermodynamic laws. An object that general relativity describes as pure curved geometry turns out to behave like a thermodynamic system. That connection between the geometry of spacetime and the statistical mechanics of heat and entropy is one of the deepest and most mysterious results in all of physics, and we still don't fully understand it. it leads directly to something called the black hole information paradox, which asks, when matter falls into a black hole and the black hole eventually evaporates, what happens to the information about that matter? Is it destroyed? Is it somehow encoded in the radiation? This question has driven some of the most intense theoretical debates of the past 50 years, and it remains unresolved. But let's pull back from the theoretical edge for a moment, because while all of this mathematics was being developed, astronomers were finding things in the sky that seemed to match. In the early 1960s, astronomers discovered quasars, quasi-stellar radio sources, objects that looked like stars but were incredibly far away and incredibly luminous. Some quasars were pouring out more energy than an entire galaxy of hundreds of billions of stars, all from a region smaller than our solar system. The only mechanism anyone could propose that could generate that kind of power from that small a volume was matter falling into a supermassive black hole. As gas and dust spiral inward, they form a disk, and friction within that disk heats the material to millions of degrees, causing it to radiate furiously before it crosses the event horizon. The energy comes not from inside the black hole, but from the process of falling in, from gravitational potential energy being converted to heat and light with an efficiency that makes nuclear fusion look wasteful. Nuclear fusion converts maybe 0.7% of mass into energy. Accretion onto a black hole can convert 10% or more. That's the power source of quasars, and it's gravity doing the work. Then came the discovery of X-ray binaries, systems where a compact object, invisible in ordinary light, is pulling matter off a companion star, and that matter is emitting X-rays as it spirals in. Cygnus X1, discovered in the 1960s and identified as a strong black hole candidate by the early 1970s, became one of the most studied objects in astrophysics. The compact object in Cygnus X1 has a mass of roughly 21 times our Sun, far too heavy to be a neutron star. It has to be a black hole. And this was the moment where black holes transitioned from mathematical curiosity to observed astrophysical reality. By the 1990s and 2000s, evidence had mounted that supermassive black holes sit at the centers of most large galaxies, including our own Milky Way. The one at our galactic center, called Sagittarius A star, has a mass of about 4 million times the mass of the Sun. Astronomers tracked individual stars orbiting it for years, watching them whip around an invisible point at tremendous speeds. And from those orbits, they could calculate the mass concentrated at the center. Andrea Ghez and Reinhard Genzel shared the 2020 Nobel Prize for this work, alongside Penrose. And then, in 2019, the Event Horizon Telescope collaboration released the first actual image of a black hole's shadow, the supermassive black hole in the galaxy M87, about 55 million light-years away, with a mass of 6.5 billion suns. That glowing ring of light, bent around the dark center, was general relativity made visible, spacetime curvature you could see with your eyes. So gravity, this gentle force that keeps your pillow pressed against the bed right now, is also the force that can curve spacetime so severely that it creates regions cut off from the rest of the universe. The same equations, the same geometry, just taken to extremes. And that's one of the things that makes general relativity so remarkable. It contains within it this enormous range, from the gentle curvature that keeps the moon in orbit to the extreme warping that creates event horizons and singularities. But black holes aren't the only surprising thing that Einstein's equations had to say about the universe. Because when you zoom out, way out, past individual stars and galaxies, to the scale of the cosmos itself, general relativity has something to say about that too. And what it says is something that Einstein found so disturbing that he called it the biggest blunder of his life. In 1917, just 2 years after completing general relativity, Einstein tried to apply his equations to the universe as a whole, and he discovered something that his equations wouldn't sit still. They were restless. The math kept wanting the universe to move, to either expand or contract. There was no stable middle ground. And this bothered Einstein enormously, because in 1917, everyone, and I mean everyone, assumed the universe was static, eternal, unchanging on the largest scales. Stars moved, sure, planets orbited, but the universe itself, it just was. It had always been there, roughly the same as it is now, and it would always be there. That wasn't even a scientific conclusion, really. It was more like a philosophical assumption, so deeply embedded that nobody thought to question it. The universe was the stage. The stage doesn't move. So when Einstein's own equations told him the stage was moving, that the fabric of spacetime on the largest scales couldn't just hold still, he didn't trust the equations. He trusted the assumption. And to fix what he saw as a problem, he added a term to his field equations. Just a small modification. A constant multiplied by the metric tensor that could act as a kind of cosmic repulsion. A gentle outward push woven into the fabric of spacetime itself, perfectly balancing gravity's inward pull, holding the universe in a delicate static equilibrium. He called it the cosmological constant, and he gave it the Greek letter lambda. Now, here's the thing about this fix. Mathematically, it was perfectly legitimate. The equations of general relativity actually allow for this term. It doesn't break anything. It's consistent with the underlying geometry. Einstein wasn't cheating. He was using a degree of freedom that his own theory provided. But physically, it was awkward. He was essentially saying that empty space itself has a built-in tendency to push things apart, and he'd fine-tuned the strength of that push to exactly cancel gravity's pull across cosmic distances. It was a balancing act, and a precarious one at that, like standing a pencil on its tip. Technically possible, but you wouldn't bet on it staying that way. And Einstein wasn't entirely comfortable with it. You can tell from his writings. He introduced lambda almost reluctantly, calling it necessary for the purpose of making possible a quasi-static distribution of matter. That phrase, quasi-static, tells you he knew it was fragile. But he published it because the alternative, a universe in motion, seemed absurd. Meanwhile, other people were actually reading Einstein's equations and taking them more seriously than Einstein himself did. One of the first was a Russian physicist and mathematician named Alexander Friedmann. And Friedmann's story is one of those quiet, almost heartbreaking episodes in the history of science, because he got the right answer and almost nobody noticed. Friedmann was working in Petrograd. This is the early 1920s. Revolutionary Russia, civil war barely over, famine, chaos. And somehow, in the middle of all that, he sat down with Einstein's field equations and solved them without the cosmological constant. He just left lambda out and asked, what do the equations predict? And what he found were solutions describing a universe that changes with time, expanding, contracting, oscillating, depending on how much matter the universe contains. These are now called the Friedmann equations, and they're absolutely foundational to modern cosmology. They describe how the scale of the universe evolves over time, how the distance between galaxies changes, how the rate of expansion depends on the density of matter and energy. Friedmann published his results in 1922 in a well-respected German physics journal. Einstein read the paper and initially dismissed it, publishing a brief note claiming Friedmann had made a mathematical error. But Friedman hadn't made an error. He wrote to Einstein, carefully explaining his work, and to Einstein's credit, he eventually retracted his objection and acknowledged that Friedman's solutions were mathematically correct. But he still didn't believe they were physically relevant. Correct math, sure. But the universe doesn't actually do that. That was Einstein's position. And then Friedman died. In 1925, at the age of 37, from typhoid fever. He never saw his work confirmed. He never knew that the universe really is expanding. He just solved the equations, published the answer, and was gone. Around the same time, independently, a Belgian physicist and Catholic priest named Georges Lemaitre was working on the same problem. Lemaitre is a fascinating figure, ordained priest, trained astronomer, studied at Cambridge and MIT, deeply devout and deeply scientific, and he saw no conflict between the two. In 1927, he published a paper that not only derived the expanding universe solutions from general relativity, much as Friedman had, but went further. He connected the math to actual astronomical observations. He looked at the data on galaxies and their velocities, and he proposed that the universe is expanding, that distant galaxies are receding from us, and that the speed of recession is proportional to their distance. He even estimated the rate of expansion. Now, Lemaitre published this paper in a somewhat obscure Belgian journal, in French, which meant almost nobody in the English-speaking scientific world read it. So when, 2 years later, the American astronomer Edwin Hubble published his landmark 1929 paper showing the same thing, that galaxies are moving away from us, and that more distant galaxies are moving away faster, it was Hubble who got the credit. And for decades, the relationship between a galaxy's distance and its recession velocity was called Hubble's law. Only relatively recently has the International Astronomical Union officially renamed it the Hubble-Lemaitre law, acknowledging Lemaitre's priority. But let's talk about what Hubble actually observed, because it's one of those beautiful moments where the universe just tells you what it's doing, if you're paying attention. Hubble was working at the Mount Wilson Observatory in California, using what was then the most powerful telescope in the world, the 100-inch Hooker telescope, and he was measuring two things about distant galaxies. First, their distances, which he estimated using a type of variable star called a Cepheid variable, stars whose brightness pulses in a regular pattern and whose pulsation period is related to their intrinsic luminosity. So if you can find a Cepheid in a distant galaxy and measure how fast it pulses, you know how bright it actually is. And by comparing that to how bright it appears, you can figure out how far away it is. Clever, right? It's like seeing a lighthouse in the fog. If you know how powerful the light actually is, you can judge the distance by how dim it looks. The second thing Hubble measured was the redshift of each galaxy's light. And this is where it gets really interesting. You know how the pitch of an ambulance siren drops as it drives away from you? That's the Doppler effect for sound. Light does something similar. When a source of light is moving away from you, the light waves get stretched out, shifted toward the red end of the spectrum. The faster the source is receding, the greater the redshift. So by measuring how much a galaxy's light is redshifted, you can determine how fast it's moving away. And when Hubble plotted these two measurements against each other, distance on one axis, recession velocity on the other, the points fell roughly along a straight line. The farther away a galaxy was, the faster it was moving away. Twice as far, twice as fast. 3 times as far, 3 times as fast. That proportional relationship is what we now call the Hubble-Lemaitre law, and the slope of that line, the rate at which recession velocity increases with distance, is called the Hubble constant. Think about what that means for a second. Every galaxy is moving away from every other galaxy. Not because they're all flying outward from some central explosion point, like shrapnel from a bomb. It's more subtle than that. It's space itself that's expanding. The distances between galaxies are growing because the fabric of spacetime is stretching. Imagine dots on the surface of a balloon as you inflate it. Every dot moves away from every other dot, and the dots that are farther apart move away from each other faster. No dot is at the center. There is no center. The expansion is happening everywhere, uniformly. And this is exactly what Friedman's solutions and Lemaitre's paper had predicted from general relativity. The equations said the universe should be expanding, and now the telescopes confirmed it. When Einstein learned of Hubble's observations, he finally accepted that the universe is not static. And he reportedly called the cosmological constant, his lambda, his fudge factor to keep the universe still, the biggest blunder of his life. He'd had the answer right in front of him, in his own equations, and he'd added an extra term to hide it. Now, here's where the story takes one of those wonderful twists that makes you appreciate just how strange the universe really is, because that cosmological constant, the one Einstein introduced and then regretted, it came back, in a big way. For most of the 20th century, cosmologists assumed that the expansion of the universe was slowing down, and that makes intuitive sense, right? Gravity is attractive. All the matter in the universe is pulling on all the other matter, so you'd expect the expansion to gradually decelerate, like a ball thrown upward that slows as gravity pulls it back. The big question was whether the universe would slow down enough to eventually stop and collapse, a big crunch, or whether it would slow down but keep expanding forever, just more and more slowly. So in the late 1990s, two independent teams of astronomers set out to measure exactly how much the expansion was decelerating. They used a particular type of supernova, a type 1A supernova, as a standard candle, similar in concept to how Hubble used Cepheid variables, but useful at much greater distances. Type 1. A supernovae are thermonuclear explosions of white dwarf stars, and they all reach roughly the same peak brightness, which means you can use them to measure distances to galaxies billions of light years away. The two teams were the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. And when they analyzed their data, they found something that nobody expected. The expansion of the universe isn't slowing down, it's speeding up. Distant supernovae were dimmer than they should have been, farther away than a decelerating universe would predict. The universe's expansion is accelerating. This was announced in 1998, and it genuinely shocked the physics community. Because for the expansion to accelerate, something has to be pushing it. Some kind of energy that acts like anti-gravity, a repulsive force that overwhelms gravity on the largest scales. And that something behaves exactly like Einstein's cosmological constant, lambda. The term he added and then called his biggest blunder. It turns out it wasn't a blunder at all. Or rather, the blunder wasn't adding it. The blunder was adding it for the wrong reason and with the wrong value. Einstein wanted lambda to keep the universe static. The universe actually uses lambda, or something very much like it, to accelerate its expansion. We now call this mysterious energy dark energy, and it's one of the deepest puzzles in all of physics. It makes up roughly 68% of the total energy content of the universe. 68%. Ordinary matter, the stuff you're made of, the stuff stars and planets are made of, accounts for only about 5%. Dark matter, which we can detect through its gravitational effects but have never directly observed, makes up about 27%. And the rest, the majority, is this dark energy, this cosmic repulsion built into the fabric of space-time itself. Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics for the discovery of the accelerating expansion. And what's remarkable is that general relativity accommodated this discovery perfectly. Einstein's equations, with the cosmological constant included, describe an accelerating universe beautifully. The math was always there. Einstein just didn't know what it was telling him. So think about where we've come. Gravity. This thing you feel right now, this gentle pull holding you against the mattress, turns out to be the architect of the universe's largest structure. It determines whether the cosmos expands or contracts, speeds up or slows down. It shaped the distribution of galaxies across billions of light years, and the equations that describe your weight on a bathroom scale are the same equations that describe the fate of the entire universe. But there's still something missing from this picture, because general relativity, for all its beauty and power, has a problem. It's a classical theory. It treats space-time as smooth and continuous. And we know that at the smallest scales, the universe isn't smooth. It's quantum. It's granular and probabilistic and strange. And when you try to combine general relativity with quantum mechanics, when you try to understand gravity at the scale of atoms and subatomic particles, things start to break down. And I mean really break down. Not in a subtle, oh, we get slightly different answers kind of way. I mean the math gives you infinities. Nonsensical, unmanageable infinities that blow up in your face and tell you nothing useful about the physical world. Here's the thing. In almost every other area of physics, quantum mechanics and the other fundamental forces play together beautifully. Electromagnetism, the force that holds atoms together, that makes light, that powers every electronic device you've ever touched, was successfully merged with quantum mechanics back in the late 1940s. The result is called quantum electrodynamics, or QED, and it's arguably the most precisely tested theory in all of science. Its predictions match experimental measurements to something like 10 decimal places. Richard Feynman, Julian Schwinger, and Shinichiro Tominaga figured out how to do it, and they shared the 1965 Nobel Prize for it. The strong nuclear force, which holds the nuclei of atoms together, got its quantum treatment in the 1970s through quantum chromodynamics. The weak nuclear force, responsible for certain kinds of radioactive decay, was unified with electromagnetism into the electroweak theory by Sheldon Glashow, Abdus Salam, and Steven Weinberg in the late 1960s and 1970s. So 3 out of 4 fundamental forces have been successfully described in the language of quantum field theory. They all fit into what physicists call the standard model of particle physics, which was essentially complete by the mid-1970s and spectacularly confirmed with the discovery of the Higgs boson at CERN in 2012. But gravity? Gravity is the holdout. Gravity refuses to cooperate. And if you think about it, this is deeply strange. Gravity was the first force we understood mathematically. Newton gave us that back in 1687. It's the most familiar force in your daily life. You don't need a particle accelerator to experience gravity. You just need to drop something. And yet it's the one force that has resisted every attempt to bring it into the quantum framework. The most familiar force is also the most mysterious at a fundamental level. So why is gravity so hard to quantize? Let me try to give you a sense of the problem, because it's genuinely fascinating. In quantum field theory, forces are mediated by particles. Electromagnetism is carried by photons. The strong force is carried by gluons, The weak force is carried by W and Z bosons. So naturally, physicists proposed that gravity should be carried by a particle too, a hypothetical particle called the graviton. It would be massless, travel at the speed of light, and have a quantum property called spin 2, which relates to the mathematical structure of the gravitational field. And at a basic level, the idea makes sense. You can write down a rough quantum theory of gravity that works at low energies, at large distances where gravity is weak. It gives you reasonable answers. But when you try to push this theory to higher energies, to shorter distances, to more extreme conditions, you start getting those infinities I mentioned. In QED, similar infinities crop up, but Feynman and the others figured out a mathematical technique called renormalization that lets you systematically absorb those infinities into a redefinition of the theory's parameters. It sounds like a trick, and honestly, Feynman himself was a little uncomfortable with it, but it works. It gives finite, testable predictions. With gravity, renormalization doesn't work. The infinities multiply faster than you can absorb them. Every time you try to fix one, more appear. The technical way to say this is that quantum gravity is non-renormalizable. And that's not just a mathematical inconvenience. It's telling you something deep. It's telling you that treating gravity as just another quantum field on a fixed background spacetime isn't the right approach. Because here's what makes gravity fundamentally different from the other forces. In general relativity, gravity isn't a force acting within spacetime. Gravity is spacetime. The curvature of spacetime itself is the gravitational field. So when you try to quantize gravity, you're not just quantizing a field that lives on a stage. You're trying to quantize the stage itself. You're trying to make spacetime itself subject to quantum uncertainty, quantum fluctuations, quantum superposition. And nobody quite knows how to do that. This is the great unsolved problem of theoretical physics. It has been for nearly a century, and some of the most brilliant minds in the history of science have thrown themselves at it. Now, the most famous attempt, the one you've probably heard of, even if you've never studied physics, is string theory. The basic idea emerged in the late 1960s and early 1970s, originally in a completely different context. Physicists were trying to understand the strong nuclear force, and a young Italian physicist named Gabriele Veneziano noticed in 1968 that an obscure mathematical formula called the Euler beta function seemed to describe certain patterns in particle scattering data. It was a curious observation, and over the next few years, people like Yoichiro Nambu, Holger Besch-Nielsen, and Leonard Susskind realized that the mathematics Veneziano had stumbled onto could be interpreted as describing tiny, vibrating strings rather than point particles. But as a theory of the strong force, string theory didn't really work out. Quantum chromodynamics came along and did a better job. String theory might have been forgotten entirely, except for something remarkable. In 1974, John Schwartz and Joel Shirk noticed that string theory naturally produced a massless spin 2 particle in its spectrum, exactly the properties a graviton would need to have. The theory was practically handing them gravity for free. Instead of gravity being the force that refuses to fit into quantum mechanics, here was a framework where gravity emerged automatically, inevitably, from the basic structure of the theory. Schwartz and Shirk proposed that string theory wasn't a theory of the strong force at all. It was a theory of everything, including gravity. Think about what that means for a second. You start with this idea that the fundamental building blocks of nature aren't point-like particles, but tiny, one-dimensional strings vibrating at different frequencies. And different vibration modes correspond to different particles. One mode gives you a photon, another gives you a quark, another gives you an electron, and one of those modes, naturally and unavoidably, gives you a graviton. Gravity isn't bolted on, it's woven in. But the theory had problems, lots of them. It required extra dimensions of space, not the 3 we experience, but 9 spatial dimensions plus 1 of time, for a total of 10. The extra dimensions would have to be curled up incredibly small, too tiny to detect with any current experiment. And there wasn't just one version of string theory. By the mid-1980s, there were 5 different consistent versions, which was embarrassing for a theory that was supposed to be the unique, fundamental description of nature. The 1980s were actually a period of tremendous excitement for string theory, though. In 1984, Schwartz and Michael Green showed that string theory was free of certain mathematical inconsistencies that had plagued it, a result so striking that it triggered what people call the first superstring revolution. Hundreds of physicists pivoted to string theory almost overnight. Edward Witten at Princeton, who many consider the greatest living theoretical physicist, became one of its most powerful champions. The mathematics was extraordinarily rich and beautiful, and it kept producing surprising connections to deep areas of pure mathematics. Then, in 1995, Witten proposed something remarkable. He argued that the 5 different versions of string theory were actually all different limits of a single deeper theory, which he called M-theory. This 11-dimensional framework, yes, 11, unified all 5 string theories and also incorporated something called supergravity, which had been developed independently. This triggered the second superstring revolution and generated enormous optimism that a complete theory of quantum gravity was within reach. But here's where the story gets complicated, and honestly, a little poignant. Despite decades of brilliant work by thousands of physicists, string theory has never produced a single testable prediction that could distinguish it from other approaches. The energy scales where stringy effects would become visible are so fantastically high, near the Planck energy, around 10 to the 19th billion electron volts, that no conceivable particle accelerator could reach them. The theory's requirement for extra dimensions hasn't been confirmed. And the landscape of possible solutions, the number of different ways you could curl up those extra dimensions, turns out to be staggeringly vast, something like 10 to the 500th power different possibilities. Each one would give you a different low-energy physics, and there's no known principle for selecting which one describes our universe. So string theory remains, as of now, a magnificent mathematical structure that might be the right answer. But we can't tell. It's like having a beautifully detailed map that might be of the right territory, but you can't check because the territory is too far away to visit. And string theory isn't the only game in town. There's another approach called loop quantum gravity, developed primarily by Abhay Ashtekar, Lee Smolin, and Carlo Rovelli starting in the mid-1980s, where string theory tries to replace general relativity with something more fundamental. Loop quantum gravity takes Einstein's insight seriously, that gravity is the geometry of spacetime, and tries to quantize that geometry directly. The result is a picture where space itself, at the tiniest scales, isn't smooth and continuous, but has a discrete, granular structure. Space comes in tiny chunks, the smallest meaningful volume being roughly a Planck length cubed. That's about 10 to the minus 99 cubic centimeters. Unimaginably small. In this picture, space is woven from a network of loops, hence the name, forming a kind of quantum foam at scales far too small to observe directly. Loop quantum gravity has its own elegances and its own problems. It doesn't require extra dimensions, which is nice, but it has struggled to show that smooth classical spacetime emerges from its quantum structure at larger scales, and it doesn't naturally unify gravity with the other forces the way string theory promises to. There are other approaches too, causal dynamical triangulations, which tries to build spacetime from tiny triangular building blocks and has produced some intriguing results in computer simulations. There's causal set theory, championed by Raphael Sorkin, which proposes that spacetime is fundamentally a discrete set of events with causal relationships between them. There's the asymptotic safety program, which suggests that maybe gravity can be quantized using conventional quantum field theory methods after all, if you look at it the right way. And then there are the clues, tantalizing, incomplete clues that might point toward the right answer. One of the most profound came from Jacob Bekenstein and Stephen Hawking in the 1970s, when they showed that black holes have entropy, AI, measure of hidden information, and that this entropy is proportional not to the volume of the black hole, but to the area of its event horizon. Think about how weird that is. Normally, if you have a box of gas, the amount of information it contains scales with the volume. But for a black hole, it scales with the surface area. This led to something called the holographic principle, developed by Gerard T. Hooft and Leonard Susskind in the 1990s, which suggests that all the information contained in a region of space can be encoded on its boundary. It's as if the three-dimensional world we experience is, in some deep sense, a projection from a two-dimensional surface. In 1997, Juan Maldacena, a young Argentine physicist working at Harvard, made this idea precise with something called the ADS/CFT correspondence, a mathematical equivalence between a gravitational theory in a certain curved spacetime and a quantum field theory without gravity living on the boundary of that spacetime. It's one of the most important results in theoretical physics in the last 30 years, and it's given physicists a powerful tool for studying quantum gravity indirectly. But the space-time in Maldacena's correspondence isn't quite like our universe. It has a negative cosmological constant, while our universe has a positive one. So there's still a gap between the mathematical playground and the real world. What's beautiful about all of this, and I think this is worth sitting with for a moment, is that gravity, this most basic and familiar of phenomena, is leading us toward the deepest questions about the nature of reality. What is space? What is time? Are they fundamental, or do they emerge from something more basic? Is information the true foundation of physics? These aren't just abstract philosophical musings. They're questions that physicists are actively working on, using mathematics and thought experiments, and increasingly, observations of gravitational waves and black holes and the cosmic microwave background. And speaking of gravitational waves, that's a story we haven't fully told yet. Because the detection of gravitational waves didn't just confirm another prediction of general relativity. It opened an entirely new way of listening to the universe. Not with light, not with radio waves, not with any form of electromagnetic radiation at all, but with the fabric of space-time itself, rippling and stretching and compressing as it carries messages from the most violent events in the cosmos. Einstein predicted gravitational waves back in 1916, just months after publishing his field equations. The math showed that if you disturbed spacetime violently enough, say, by accelerating a massive object, the disturbance would propagate outward at the speed of light, like ripples spreading across a pond. But Einstein himself went back and forth on whether these waves were real physical phenomena or just mathematical artifacts. He actually wrote a paper in 1936 arguing that gravitational waves didn't exist, and it was only after a reviewer, who turned out to be Howard Percy Robertson, pointed out an error in the calculation that Einstein corrected course. Even then, the physics community argued about it for decades. It wasn't until a famous conference in Chapel Hill, North Carolina, in 1957 that the debate was largely settled, when a young physicist named Richard Feynman, yes, the same Feynman from quantum electrodynamics, presented a beautifully simple thought experiment. Imagine, he said, a couple of beads on a stick. If a gravitational wave passes through, the beads will slide back and forth on the stick, and friction will generate heat. That heat is real energy. So the wave must be real. It's called the sticky bead argument, and it convinced most of the holdouts. But knowing gravitational waves exist and actually detecting them are two very different things. The problem is that gravity is absurdly weak compared to the other forces. Even the gravitational waves from cataclysmic events, two black holes smashing into each other, neutron stars colliding, produce incredibly tiny distortions by the time they reach Earth. We're talking about changes in distance smaller than 1,000th of the diameter of a proton. That's not a typo. 1,000th of a proton. To measure something that small, you need an instrument of almost inconceivable precision. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory. The idea goes back to the 1960s and 1970s, when physicists like Joseph Weber at the University of Maryland started trying to detect gravitational waves using large aluminum cylinders that would, in theory, vibrate when a wave passed through. Weber actually claimed to have detected gravitational waves in 1969, and it made headlines around the world. But other groups couldn't reproduce his results, and the consensus eventually formed that his detections were spurious. It was a painful episode. Weber spent the rest of his career defending his results, increasingly isolated from the mainstream. But his work inspired others to think seriously about detection. And by the early 1970s, Rainer Weiss at MIT had sketched out a much more promising approach: laser interferometry. Here's how it works, and it's genuinely elegant. You build two long arms at right angles to each other, like a giant L. You send a laser beam down each arm, bounce it off a mirror at the far end, and bring the two beams back together. When the beams recombine, they create an interference pattern. The waves of light either reinforce each other or cancel each other out, depending on whether the two arms are exactly the same length. Now, if a gravitational wave passes through, it stretches space along one arm and compresses it along the other. That changes the relative length of the arms by a tiny, tiny amount, which shifts the interference pattern. You're essentially using light as a ruler to measure the stretching of space itself. The concept is simple. The execution is anything but. Weiss, along with Kip Thorne at Caltech and later Ronald Drever, also at Caltech, spent decades pushing the technology forward. The mirrors had to be the smoothest, most precisely shaped objects ever manufactured. The laser had to be extraordinarily stable. The entire apparatus had to be isolated from every conceivable source of vibration: passing trucks, ocean waves hitting distant coastlines, even the quantum jitter of the atoms in the mirrors themselves. LIGO's arms are 4 kilometers long, and there are two identical detectors, one in Hanford, Washington, and one in Livingston, Louisiana, separated by about 3,000 kilometers, so that any real gravitational wave signal would show up in both detectors with a slight time delay, while local noise would not. Construction began in 1994. The initial version of LIGO ran from 2002 to 2010 and detected nothing, which was actually expected. The sensitivity wasn't quite good enough yet. Then came a major upgrade called Advanced LIGO, which improved the sensitivity by about a factor of 10. And on September 14, 2015, before Advanced LIGO had even officially started its first observing run, both detectors picked up a signal. A characteristic chirp rising in frequency and amplitude over about 0.2 of a second, then cutting off abruptly. When the team analyzed the waveform, it matched the prediction for two black holes, each about 30 times the mass of the Sun, spiraling into each other and merging into a single black hole about 62 solar masses. The missing 3 solar masses radiated away as pure gravitational wave energy. In that fraction of a second, the collision released more energy than all the stars in the observable universe combined. Think about that. All the stars, all of them. And we heard it from over 1 billion light years away, as a tiny shiver in the length of a 4-kilometer tunnel, a change of about 4/1000ths of a proton diameter. The announcement came in February 2016, and it was one of those rare moments in physics that felt historic even as it happened. Weiss, Thorne, and Barry Barish, who had taken over as director and turned LIGO from a struggling project into a functioning observatory, shared the 2017 Nobel Prize in Physics. But here's the thing. LIGO wasn't just a one-hit wonder. In August 2017, LIGO and its European counterpart Virgo detected gravitational waves from something different, 2 neutron stars merging. And because neutron star mergers produce light, as well as gravitational waves, astronomers around the world swung their telescopes toward the source and observed the aftermath across the entire electromagnetic spectrum: gamma rays, X-rays, ultraviolet, visible light, infrared, radio. It was the first time an astronomical event had been observed in both gravitational waves and light. Multi-messenger astronomy, they called it, and it was like suddenly gaining a whole new sense. For all of human history, we'd been watching the universe. Now, we could listen to it too. And what we heard told us things light never could. The neutron star merger confirmed that such collisions are where many of the heaviest elements in the universe are forged: gold, platinum, uranium. The gold in a ring on your finger was likely created in a neutron star collision billions of years ago, flung out into space, eventually incorporated into the cloud of gas and dust that became our solar system. Gravitational waves helped confirm that. Since then, LIGO and Virgo have detected dozens more events, black hole mergers of various sizes, more neutron star collisions, even a few events that might involve a black hole swallowing a neutron star. Each detection teaches us something new about the population of compact objects in the universe, about how massive stars live and die, about the behavior of matter at densities we can't replicate in any laboratory. And the future is even more exciting. The next generation of ground-based detectors, projects like the Einstein telescope in Europe and Cosmic Explorer in the United States, will be 10 times more sensitive than advanced LIGO, able to detect mergers from when the universe was young. And then there's LISA, the Laser Interferometer Space Antenna, a joint European-American mission planned for the 2030s that will put a gravitational wave detector in space with arms 2.5 million kilometers long. Lisa will listen to a completely different frequency range, picking up signals from supermassive black hole mergers, from thousands of compact binary systems in our own galaxy, maybe even from the gravitational echoes of the early universe itself. And that brings us to something genuinely profound, something that connects back to almost everything we've talked about tonight. Because if we can detect gravitational waves from the very early universe, from the first fraction of a second after the Big Bang, we might be able to test ideas about quantum gravity directly. During that earliest epoch, the universe was so hot and so dense that quantum effects and gravitational effects were both important simultaneously. The gravitational waves produced during that era would carry an imprint of whatever the true quantum theory of gravity turns out to be. They'd be a message from the moment when spacetime itself was being born. We're not there yet. Not even close, really. But the tools are being built. The mathematics is being developed. And the questions, those beautiful, vertiginous questions about what space and time really are, about whether the universe is fundamentally made of information, about whether gravity is truly a force or just the geometry of existence. Those questions are sharper and more tractable than they've ever been. You know, it's worth stepping back for a moment and appreciating the arc of what we've been talking about. We started with the ancient Greeks, with Aristotle watching heavy things fall and concluding that they were seeking their natural place at the center of the cosmos. A reasonable idea, beautifully wrong. Then Galileo, rolling balls down inclined planes, measuring, timing, insisting that nature speaks in the language of mathematics. Newton, sitting in that garden in Woolsthorpe, maybe watching an apple, maybe not, and realizing that the force pulling the apple down is the same force holding the moon in its orbit. One law, universal, stretching across all of space. That was a revolution in how humans understood their place in the universe. And then Einstein, that young patent clerk in Bern, daydreaming about falling off a roof and realizing that gravity isn't a force at all. It's the curvature of space-time, shaped by mass and energy, telling matter how to move. A theory so strange and so beautiful that it predicted things Einstein himself could barely believe. Black holes, gravitational waves, the expansion of the universe, the bending of starlight, and every prediction, one by one, over the course of a century, confirmed. Schwarzschild solving the equations in the trenches of World War I and finding the geometry of a black hole, then dying before he could see what his solution would mean. Eddington chasing an eclipse to prove that starlight bends. Hubble watching galaxies fly apart. Penzias and Wilson hearing the echo of the Big Bang in their radio antenna. Perlmutter and Schmidt and Rees discovering that the expansion is accelerating, driven by something we still can't explain. And then, in 2015, that tiny shiver in a laser beam in Louisiana, carrying news of two black holes that collided 1 billion years ago. Every step of this story was built by real people. People who were confused, who made mistakes, who argued with each other, who sometimes got it spectacularly wrong before getting it right. People who stayed up too late scribbling equations, who built instruments of impossible precision, who stared at data until patterns emerged from noise. The story of gravity is the story of human curiosity at its most relentless and its most humble, because every answer opened up deeper questions, and every generation discovered that the universe was stranger and more wonderful than the one before had imagined. And here we are, right now, in one of the most exciting moments in that story. We have a theory of gravity, general relativity, that works magnificently across an enormous range of scales, from the solar system to the large-scale structure of the cosmos. And we have quantum mechanics, which works magnificently for everything else. And they don't fit together. Not yet. The reconciliation of these two frameworks, the theory of quantum gravity, whatever it turns out to be, will almost certainly change our understanding of space, time, and reality as profoundly as anything Newton or Einstein ever did. Maybe more. But that's a problem for tomorrow, or for the physicists and mathematicians who are working on it right now, in offices and on chalkboards and in computer simulations around the world. For tonight, it's enough to know that gravity, this quiet, gentle, omnipresent thing that's holding you against your mattress right now, that's keeping the moon in its orbit and the Earth on its path around the sun, that's pulling galaxies into clusters and clusters into superclusters across billions of light years, is also the deepest puzzle in all of physics, the most familiar force in the universe, and the least understood. And isn't there something lovely about that? That the thing you feel most directly, most constantly, most intimately, the gentle pull of the earth beneath you, the weight of your own body settling into the bed, is connected to the biggest unsolved questions in science. You're lying in a gravitational field right now. Space-time is curved around you, ever so slightly, shaped by the mass of the planet beneath you. And that curvature, that gentle, invisible geometry, is the same phenomenon that bends light around black holes, that sends ripples through the fabric of reality when neutron stars collide, that shapes the entire large-scale structure of the cosmos. It's all one thing, one beautiful, mysterious, endlessly fascinating thing, and we're still figuring it out. But we've come so far, from Aristotle's falling stones to Einstein's curved space-time to the chirp of merging black holes heard by lasers in the Louisiana swamp. What a journey! What an extraordinary, improbable, deeply human journey. So let that settle over you. Let the weight of your body against the bed be a reminder, not of something mundane, but of something profound. Gravity is holding you. It's been holding you your whole life. It held Newton and Einstein and every person who ever looked up at the stars and wondered why things fall. And it will keep holding you, gently, quietly, while you drift off to sleep. The universe is curved, and you're resting right in the curve of it. And that's a beautiful place to be.